Hi, everyone. Thank you for coming. This is what we are gonna, so my name is Jose Castroleon, and he is Spiros. Both were working in the cloud team at CERN, and what we are gonna, it doesn't change. Anyway, is on how to improve the resource availability at CERN, how we can get more and more resources available to our end users, and how we're gonna get more performance to them. So we are gonna, okay, this is gonna be funny. No, it's not on purpose. Yeah. Okay, we are gonna do a brief introduction of what we do at CERN. It's even worse. Okay. Check one thing.
They have this problem earlier in this room, like they stop the cables and try
anything. Yeah, I changed the other one. Okay. Okay, I see the slides, so that's fine. Yeah, I think we can change the screen. So what we are gonna talk about is on what we do at CERN, how we build the CERN cloud, CERN private cloud, and just getting into details, how we get the most of the resources that we have available, how we are doing automation, how we are doing optimization, looking into spot or preemptibles, and doing containers on bare metal. So we work for the European Organization for Nuclear Research. That is the world's largest particle physics laboratory, founded in 1954, and we have now 23 member states, with the addition of Serbia like last month. And what we do is fundamental research in physics. And you can see there the map, sometimes, the worldwide map with all the countries that are doing collaborations with us. And also a small snippet of the accelerator complex. This is what our colleagues, the physicists at CERN, they are using. So this accelerator complex, from ionized gas that we inject in it, then the particles, before everyone knows about the LHC, and we are collecting particles there, but then the particles, they will initiate in one of the linear accelerators, and they will go through the whole history of accelerators at CERN. So they will go through the booster, the proton synchrotron, the super proton synchrotron, and then they will end up in the LHC when they collide, and they produce a huge amount of data. We have another one that's just over there. There's the antiproton decelerator. It's the one that is like close by to where I work and where the Spiros work. So to get an impression of the size of the complex, this is kind of a view of the whole setup. So we have the two sites, CERN Megan and CERN Prevesan, and you can see the four experiments: Atlas, Alice, CMS, and LCV. We are located in the border between France and Switzerland. And you can see there the Geneva Lake, and also the airport. This is kind of the ring. But then we are not going to talk about the CERN only. We're going to talk about the cloud service. So we started in production in July 2013. We offer an infrastructure as a service to our end users. All the control plane and hypervisors that we have are based on CentOS 7. And we have two data centers, one in Geneva, one in Budapest. Around 9,000 servers that we have deployed, they are organized in around 70 cells. One thing that is new from the Berlin summit is that we just added a second region to the service, and we are running Rocky. So we have started to look at the Stein packages and backporting and moving our services there. So if you look at the status of the cloud, now it's fine. Okay, cool. We have around 300,000 cores. Okay. So we have 300,000 cores, around that. In, as I said, 8,000, 9,000 hypervisors, 35,000 VMs. And you can see here in the bottom chart, there's the rate of VMs that are created and deleted. So in there, we have a mixture of things. It's our users of the cloud, our experiments that are using in the workflows creation and deletion of VMs continuously. And also our own internal testing, we are using Rally, that continuously triggers and creates machines all the time in the service. Back in time when we started with the service in July 2013, we only offer VMs. This is the kind of the very basic configuration that we started. And since then, we have been adding more and more resources. So this is the picture right now of the services that we have deployed. Okay, so it's not only offering VMs. Now we have physical machines. We have different kinds of storage that we offer to the VMs. We have clusters, container clusters that we have on top. We offer network services. This is more or less kind of the picture at the moment. If we go back in time, when we decide to build the cloud in 2012, it was the first. So it was in the long shutdown 1. That is kind of where the arrow is, and in there, it's like it's only the kind of the moments that we can change the whole deployment, because during the run, when the accelerator is running, we cannot do major changes of the setup. We need to keep the service stable. So at that time, we were able to. We're looking into what are the performance requirements for the future. You get there, their expectations were like that. We knew that the team size was fixed, so we need to improve the system or the way we manage the data center. So what we did was we started a project at CERN that focused in 3 core areas into how we are going to provision resources, how we are going to configure them, how we're going to monitor them. And we start with the motto of all the servers shall be virtual. So we do, at that time, we were kind of lending over physical machines, but then we started with the abstraction of having only VMs. So if we look at now, the cloud has more than around 300,000 cores. We have been adding more and more services. We are continuously improving the existing ones. One thing that has been kind of the same is that we have the same amount of staff managing the cloud. The cloud is like several orders of magnitude bigger, and we have the very same team. What we are looking at, because the expectations from the experiments are exactly the same, if you see, it's kind of way beyond what we can achieve just by buying hardware. We are focusing in 4 different areas at CERN. One is try to make the code as much efficient as possible, so it can be run in less nodes. Improving algorithms, and now for that, our colleagues of the physics department are looking into machine learning of those algorithms, trying to find ways of improving them. They are also using GPUs and FPGAs to speed up the software. And kind of our duty was try to get the most of the hardware that we have and get the most resources available to them. And this is what this presentation talks about, into ways to evaluate the status of the cloud, find places in which we can improve the cloud service, develop those solutions, and make them available. So with two main objectives. One is getting the most performance solution for our users and getting the most amount of resources. What we are going to talk about is to this for, let's say, projects. So we're going to talk about Mistral for doing automation, Watcher for doing optimization, Preemptibles with Aardvark, and bare metal on containers. So if we look at the picture of how we do automation at CERN, these are kind of the components, OpenStack components that do automation. We have Mistral that interacts with all the business logic in terms of resources. And we have on the right-hand side on what you're looking at, that is you have all the monitoring data and how we are we're using the monitoring data to optimize the cloud with Watcher. So the main objectives of automation, what we look at automation at CERN, is just that we don't need to care about what the automation does. What we need to care is to get the most performance. So we focus, cloud team focus on getting the last bit of performance of the CPU, of the VMs. And then Mistral, in this case, will take all the heavy hurdle to automate the stuff behind the scenes, focusing on optimizing the user experience. And for that, we are doing two things. One is cleaning orphan resources, and the other one is expire unused resources. So for that, it's like something that is kind of quite specific to our cloud deployment, that we don't have it outside, so that we don't have it kind of in a typical public cloud, is that we have two kinds of projects. These projects are basically fitting the two things I was mentioning. So the share projects will be used for compute and production use cases. And the idea is to track the resources there, and they are not orphaned. So someone is there behind the scenes managing the service. The personal, what they try to cover, is like that we clean up resources that are for private users, and then those are kind of properly decommissioned. The only change since the last summit is the addition of the multi-region support, because we have it since a while. So I saw this slide in the Berlin summit. So we are using Mistral for that. We have a set of workflows, or workbooks, and they are integrated into each other to do the kind of the business logic to clean up resources kind of hierarchically. What we did, because we added the second region, was to look at, in each of individual elements that clean up resources, they look up what are the regions available for that particular service and do the cleanup kind of in each of them. So that when for example, it runs on the S3 side, it will clean up all the resources that are on S3 in all the regions available. So this is kind of a small effort on deployment, so on preparing that. But then the thing is, at the moment, if we have 2, 3, 4, or 5 regions, it's the same. So for us, it's one hard work for making it work, but then after, it pays off. If you want to look at what is behind the scenes, is just this massive query. So what it does is it checks the catalog, checks for the services that are in the catalog that match that type, and finds the ones that offer a public interface. Very basic operation with the catalog, and there's a loop on those. Okay. The other part is to clean up resources. So in this case, what we have seen over time on the personal part, it was like each user has a small quota of 5 instances and 10 cores. We have around 3,600 users, so it means that we have laid over like a quota for 15,000 VMs. Actually, don't tell anyone, but then we don't have quota for those, but that's just a comment. So then what we look at is just to make sure that these resources are properly used. So what we have done is like each VM that is deployed has an expiration date, so that we configure on creation. This is like set it up as a Nova tag. And then it's like the user needs to renew it to keep the machine running. And as we want to remind the users that this machine is gonna expire, we send mails 30 days, 3 weeks before, 2 weeks before, 7 days, 5, and so on, so on, so on, until the machine gets expired. And this is implemented as a workbook in Mistral. And if you can, so the thing is, we deployed, it was at the beginning of last year, and after 6 months, we were able to recover 3,000 cores of unused resources. That is like 100 servers that can be used for something else. Okay. So now I'm going to talk about how we are optimizing things. And we evaluate a project, the project called Watcher, that is the optimization service in OpenStack. We started with evaluation during last year in August. And it turned out that it was working. So the basis of this service is like it looks at monitoring data, it looks at information from the Nova instances, how they are deployed, how they are laid out, and then it aggregates those information and tries to do an audit. So based on that audit, then you can see if like, okay, probably it's like unbalanced in one side, so if you want to optimize this solution, then I move the machines on the other side to improve the perceivedness of performance. What we saw during that evaluation, it was like the way it was implemented didn't fit to run it at scale. So, so the first thing is it was trying to do, so by default it does hypervisor list. If you try to do hypervisor list with 70 cells and 36,000 VMs, it doesn't work. It takes a while. So what we have been doing was try to find ways to optimize those calls. So try to see on ways to execute it at scale. For the monitoring side, we are not using kind of the default plugins they offer. So they offer plugins for Monasca and Gnocchi, as we are not using any of those. So we are looking into ways to improve the data sources that this project provides. And other things like later on is like once you do an audit, then you have kind of a strategy on how you are going to fix, so how you're going to optimize that workload. And we are looking into ways to optimize those strategies. And for that, we have different use cases. So for example, what we can do is like do an audit on a cell and see how this is balanced or not. I'm not talking, I mean, the Nova scheduler does a great job of placing the machines where if you give them kind of the proper settings, it will balance the cluster. But this is an allocation. The thing is, you don't know which is kind of the user of CPU that you have behind, and probably the picture that the CPU usage could be like the one I show below. We have servers that are way overcommitted and servers that are idle. And the ideal case would be like just see if we can move things around, if that perceivedness of performance will be better for the end user. So the idea is to do an audit on in each of the cells and try to discover performance issues. Try to find the noisy neighbor, try to find all this stuff, so then we can do, we can trigger automations in advance. And since quite a while, we are using, we have environments with hyperconverged servers in which we merge CPU and storage in the same box. And the idea there was just because you need to give some space for the I/O processes. You need to balance and leave some headroom. And in that case, what we can do with that setup, as all the VMs there are like a boot from volume, then you can move things around quite fast and do it kind of continuously. And this is kind of what we are working on. But we have all the strategies that we are working on. One is we procure hardware normally twice a year. And then we have this kind of picture in which we commission all this hardware to production, and the users are starting to create machines, and then they start to fill up the resources. You have to ramp it up. It will be production for quite some time, and then when we need to decommission the servers, we need to do the same thing. We are notifying the users. It will delete their VMs, move them some whatever, but then we have a longer tail to decommission the resources. So the idea is to place, we have these unused resources, that is money that we need to focus on getting resources there. And the idea is that you can put preemptible VMs there. So you can fill the gap, use those resources for the life of the server, and increase the capacity. And what we target is to have an automatic audit in Watcher that adds preemptibles on the fly. And for that, we are using the Boeing workloads. In this case, LHC at home. So if everyone, does anyone know what is Boeing or LHC at home? Okay, so this is just an extra advertisement. If you want to contribute with LHC computing, what you can do is, there is like a, Boeing is like if you know SETI at home, it's kind of the same concept. We'll use your spare cycles of your laptop, computer, or whatever, and we'll download some analysis of the LXC, some data from the LXC. We will compute it and give it back to the service. So this is what we want to do with these, with the ramping up and tail down, to fill those gaps with Boeing workloads that are backfilling the LHC at home Boeing service. So this is the status of the service at this moment. We have been adapting the, providing some input for the audit scope. The audit scope is a way to send an information to Watcher to only focus on a specific availability zone, on a specific aggregate. So with that, we'll narrow down the queries to get information about the hypervisors. On the data sources, all the data that we have comes from collectd. Collectd is storing then in InfluxDB, and we have many instances of InfluxDB. So in order to kind of have a single access layer to those many instances, we have a Grafana proxy. And this is what we are adding back to the community. We are adding this data source Grafana proxy that you can use then later. And we are working on these strategies. So the per cell workload balancer with the audit, so the one that comes with Watcher, just by modifying the audit scope, it works out of the box. So we can use it from now. And what we are working on is on make the balance, the strategy for doing the balancing the hyperconverged server and the preemptible scheduler. And then I pass to my colleague.
Thank you, Jose. I have like 5 or so minutes, so I'll try to be a bit quick. I will talk about the Aardvark, which is the code name of a small engine that we created to work in conjunction with Nova to offer preemptible instances. And I will say a few things about running bare metal in containers with Magnum. So what are preemptibles? Some of you might know what are spot instances in AWS or preemptible instances in Google Cloud. These are resources that have low priority in the cloud, and they are much cheaper, and they can be preempted, meaning deleted at any time if the cloud needs them for higher priority workloads. In AWS, you just bid what you want to provision, and in Google Cloud, VMs are recycled every 24 hours. In a public cloud, you can implement the same strategy in the scheduler that we wrote, but for a private cloud, as we have, it's not a matter of cost. It's mostly a matter of availability for, let's say, more important customers. So user VMs are usually experiment VMs or service VMs, meaning standard IT tools that must not be preempted and must be available at all the time. But since we are a private cloud and we work with quotas, sometimes we over provision quotas, and users end up not consuming them, so there is free capacity. This capacity can be filled up with preemptible workloads, meaning these are projects that have a special property in their metadata, and they have access to some special flavors that are for preemptible machines, and they spawn machines in the cloud where there is space until the cloud is full or reach up to a certain point, like 95-19% utilization. Then when a more important workload comes along and hits no valid host, or there is no capacity in the cloud, this scheduler will try to preempt these resources and create more free space, and then it will try to rebuild the VMs, the user VMs. All this was explained very well in the presentation that our colleagues Belmiro and Theodoros did in the last summit in Berlin. We have put the link to the video with a live demo in our production cloud. It's very cool, go watch it. And what is the status of this project? So the specs, there are two changes in Nova, and Nova will be actually agnostic of what preemptibles are. But there are two changes that we needed to do. One is to introduce a pending state, which is approved, and one is to rebuild instances in cell 0. This is an internal detail, it's not user-facing. And the spec was approved, but needs to be reapproved, and the code is work in progress at the moment. Users of this service will be, as Jose mentioned, LHC at home with Boeing workloads and the opportunistic batch. This will be consumed by the batch service, and they will create resources added to their batch farm for certain workloads that are not important and can be preempted, and maximize the utilization of our cloud. The second topic is containers or bare metal. So a way to improve resource capacity, resource availability is to remove the virtual machine tax. So instead of having a 3 to 5% penalty because of KVM, you can just run your workloads directly on the physical machines and use containers for some basic isolation. For orchestrating containers in our cloud, we heavily use OpenStack Magnum, which is a small API service that orchestrates Kubernetes and Docker Swarm on OpenStack. And traditionally, it started using only virtual machines for compute nodes, for like worker nodes. But now we added also support for physical machines. So you can start the control plane of Kubernetes or Docker or Swarm in virtual machines, which could be small and a couple of virtual machines, and then all the workers can be physical machines and have a 0% penalty. Another option, because usually when you manage physical infrastructure, it might be in a separate data center or even have different regions that you cannot spawn a cluster across the regions. Another solution that we are working on, which is, let's say, purely Kubernetes, is to federate Kubernetes clusters and create very big compute batch farms. So again, the users of this service is the batch service, which is the most compute-intensive workloads that we have at CERN, apart from the trigger farms, and they are leveraging mostly clusters with physical workers to orchestrate HT Condor, which is a batch system from the 90s, but they are also investigating other ways of submitting jobs either directly to Kubernetes or through Condor. Regarding the OpenStack integration, everything is complete from the OpenStack point of view. So if you have Ironic and Magnum deployed, you can just use it and have a similar setup like the one that we have. And for the last, we left a small plug that we have. We recently created a blog post to post technology-related things that we do at the cloud team. Before it was only for OpenStack. Now it's more generic. The two topics that we already covered in this presentation are the bottom two, which is the expiration of VMs in the cloud using Mistral, and the other one is using preemptible VMs to maximize the utilization of the cloud. But the last two additions that our colleagues worked on it, and soon they will prepare presentations, is splitting the cloud without downtime in two regions, which is a very interesting exercise. And another one was to backfill, again with Boeing and compute workloads, empty Kubernetes clusters using a Helm chart. So this one, you can just check the blog post. There is a chart available, and it's very easy for you also to contribute if you have spare capacity. This is our contacts and links to our Git repos that we have in our GitLab and tech log. That's it. If you have any questions. Yes.
Please use the microphone, please. Can you?
I can repeat the question.
Okay, fair enough.
What size team do you have actually to maintain the infrastructure and develop it in the ways you've spoken about?
For operations, it's 5 or 6 are the core team, and there is 7 or 8 more people which are trainees or staff that recycles every 2 years or every 1 year. But we have also additional teams to manage storage and databases, for example, separately.
Yeah. So the thing is, the core team is still the same, and the people that are doing development, so the other people that we have around, they are focusing more on development on different areas that we are interested in. So they are not. They are also doing their kind of fair share of support, but kind of the team is pretty small.
Okay, thank you.